Hello and welcome back to another episode of Physics Partner. What do a garden hose, a roaring river, and the blood flowing through your veins have in common? They all obey one of the most fundamental principles in physics, the continuity equation. At its heart, this concept is surprisingly simple, built on the conservation of mass. It states that for a steady fluid flow, the mass flow rate remains constant. This is captured by the equation you can see on the screen, where ρ represents density, A is the cross-sectional area, and V is the fluid's velocity. You can see the more details about this equation here on your screen. For incompressible fluids like water, this simplifies further. If the area decreases, the velocity must increase and vice versa. This principle is critical across numerous fields. In medicine, ultrasound technology uses it to measure blood flow velocity and detect potential blockages in arteries. Civil engineers rely on it to design bridges and dams, predicting water flow and pressure to ensure structural integrity and prevent catastrophic failures. Meteorology applies it to understand air movement, which is vital for forecasting weather patterns, for daily rain to major events like hurricanes. Without this equation, many modern technologies and safety measures would be impossible. We encounter the continuity equation in everyday life. When we squeeze the end of the garden hose, you decrease the area, forcing the water to shoot out with greater velocity to maintain the flow rate. It can even be seen in traffic flow. When highway lanes merge, the density of cars increases, and to avoid pileups, the velocity of the traffic must slow down. Similarly, a river flows much faster through a narrow gorge than when it widens into a broad plain because the same volume of water is forced through a smaller area. It's important to note that the basic equation makes assumptions such as an incompressible fluid and a perfectly steady flow. Reality is often more complex, with compressible gases like air and turbulent flows requiring more sophisticated versions. However, the underlying principle of mass conservation always remains the same. Looking to the future, advanced forms of the continuity equation are fundamental to computational fluid dynamics, which is used to simulate everything from blood flow in artificial organs to the aerodynamics of more efficient airplanes. The integration of AI and machine learning promises to further revolutionize our understanding of fluid dynamics. Ultimately, the continuity equation is a simple concept with profound implications governing the flow of the world around us. So I think it's enough for today. So thank you very much for listening and watching. I hope you enjoyed the video. I hope this video is useful for you. So take care of yourself and don't hesitate to write an email if you have any question, query, suggestion, and even classes are required. Take care of yourself meanwhile. See you in the next video. Goodbye.